Thanks for coming. I'm Alex Gaynor, and this is Quantifying Memory Unsafety and Reactions to It. I'm a founder and principal at Fish in a Barrel. Fish in a Barrel is a satirical security consultancy and real collective of folks doing security research. I've also had normal jobs, including as tech lead for Firefox Sandboxing and as chief information security officer for an election data startup. At Fish in a Barrel, we've discovered hundreds of security vulnerabilities in widely used open source projects. As our name suggests, our focus is on attack surfaces where finding vulnerabilities is like shooting fish in a barrel. To identify them, we look for places where there's a common underlying cause of a lot of vulnerabilities, and they're being handled with a game of whack-a-mole, rather than by actually treating the root cause. Let me give you an example. You may recognize this screenshot. It's the phishing email from March 2016 that John Podesta received. John clicks on the link, after he's told it's safe by an IT staffer, and then 7 months later, the contents of his inbox is a front-page story in every newspaper in the country. Credential phishing has been recognized as a security challenge for decades, and the way we've treated it was heavily centered around user education and email filtering. We've told users to closely check the sender, not to click on links in emails, and we've sent them fake phishing emails to test them. And to a lesser extent, we've worked on technologies like SPF and DKIM. However, even these technologies mostly serve to better enable humans to recognize phishing emails. However, all these miss the common underlying cause of credential phishing. Credentials that are replayable and not origin-bound, meaning you could obtain credentials on one domain, a phishing page, and use it on a victim website. And because we've never addressed the root cause, no matter how much we trained users, credential phishing remained endemic, leaving a gap big enough to drive a presidential election through. WebAuthn and its predecessor U2F, colloquially known as security keys, changed the game here by actually addressing the lack of origin binding in credentials. And you can see it in the results. Google's research shows that credential phishing against users with security keys has a 0% success rate. Not like 0%, not close to 0%, actually 0%, even against the most sophisticated attackers. This is the kind of success that we can achieve by focusing on root causes and not merely playing a game of whack-a-mole with symptoms or proximate causes. This is what Fish in a Barrel means when we say security must focus on addressing underlying causes. And so we support these efforts with evangelism and by distributing security keys to groups at heightened risk, such as political campaign teams. This brings us to the central topic of this talk, memory unsafety. We believe memory unsafety in widely used programming languages is one of these root causes. We think that for far too long, our industry's approach has been to play whack-a-mole with an unending series of ASAN and MSAN reports while ignoring this root cause. I want to walk you through a definition of memory unsafety, a few case studies that we believe demonstrate the need to treat this as a root cause, and then I want to share with you what we've learned in trying to talk about this issue to software and security engineers. Memory unsafety is a property of programming languages, and our definition of memory unsafety is a really practical one. They're programming languages where, by default, you can get these vulnerability types: buffer overflows, use after freeze, wild pointers. You'll recognize these as the classic bug types you'll find in a C program with valgrind or ASAN, and that's not a coincidence. Here's a list of programming languages, grouped by whether they're memory safe or memory unsafe. A few things are important to note about the languages here. While the memory unsafe languages are all pretty similar in the set of problems you might use them for, systems programming, the memory safe languages are far more diverse. Some are high level, others are low level. Some are garbage collected, some aren't. Some are interpreted, others are compiled, and of course neither of these lists are comprehensive. Not all the memory-safe languages, therefore, are necessarily good replacements for projects you might write in one of the memory-unsafe languages like C or C++. A few of them are, though. Go is a particularly good choice for network servers. Swift is excellent if you're in the Apple ecosystem, and they're trying to make Swift on the server a thing too. Rust is probably the strongest choice for a general-purpose C and C++ replacement language, and it's also able to interoperate with them. 10 years ago, it was not the case that we had several excellent competitors to C and C++, and it's important to consider that when asking how we got here. There are, however, several edge cases. For example, Go allows for data races in its map data structure. One of the features that several of these modern memory-safe languages have is an unsafe keyword that acts as an escape hatch. Some folks fear that this means that all programs in these languages merely degrade into one giant unsafe block. But in practice, that's not what we see happening. In fact, unsafe blocks do a lot to enable auditability of code bases. A research team found that of code on the Rust packaging website, crates.io, 3/4 of packages had no unsafe code at all. Looking at Rustless, a complete TLS implementation in Rust, and its complete dependency tree, the only unsafe code at all is in Ring, the implementation of low-level cryptographic algorithms. Nowhere else in their dependencies, including in the TLS protocol, is there unsafe code. And all of this matches my personal experience, that unsafe code is relatively rare, and where it does exist, enables auditors to focus on spending their time well to look for vulnerabilities. Conventional wisdom for a long time has been that exploitation of memory-unsafety vulnerabilities in real-world exploits has been the exclusive domain of Tier 1 nation-states by advanced intelligence agencies for targeted intelligence collection. This is not the case. China exploited iOS 0 days against everyone who visited Uyghur websites. NSO's Pegasus product has been found used against everyone from Middle Eastern human rights advocates to Mexican nutritionists. The exploits listed here target different software, iOS, Android, WhatsApp, Windows, and Linux servers. They're used against different populations spanning the entire globe. They represent government attackers, commercial exploit vendors, and script kiddies. The common thread here is that for each of these, the vulnerability that was exploited, or in some cases, at least one of the vulnerabilities in the chain for multi-vulnerability chains, was only possible because of the victim software being written in a memory-unsafe language. Put another way, if the relevant portions of these projects were written in a safe language, the vulnerabilities exploited here wouldn't have been possible. And that's the success criteria I set for myself in this effort. Can we make exploiting software vulnerabilities to enable human rights abuses impractical or impossible? So I've given you the premise and I've told you our argument. These vulnerabilities all share a common root cause in these programming languages' memory unsafety. If we use safe languages, we could dramatically improve computer security. Now I want to walk you through the evidence to support this claim, as well as why we think this is a tractable project to engage in. I'm going to do this in a slightly unusual way, though. Fish in a Barrel has been engaged in advocacy efforts for several years. I'm going to share with you the arguments we make and the data we marshal to support them, as seen through the opposing reactions we get. I'll be doing my best to engage seriously with the arguments against us, and I'll be framing this through the stages of grief. The first stage of grief is denial. This is generally characterized by software engineers believing that there's no reason to support the idea that there might be an underlying condition in these programming languages. People at this stage often express that it's possible to have vulnerabilities in any language, and that logic vulnerabilities are common. We argue against this using data to ground our beliefs. And here's the data we've collected over the last several years. This reflects a mix of our own analysis and analysis from the vendors themselves. One of the things we try to make clear is that the idea that memory unsafety produces vulnerabilities is an empirical claim. If you want to reject it, you need competing data. We're more than happy to revise our hypothesis, but doing so needs data, not conjecture. Most of the data here reflects individual vulnerabilities found in these projects. Data on complete exploit chains isn't quite as common because complete exploit chains are rarer in public research. However, looking at one sample dataset of complete exploit chains from Pwn2Own 2019, every single chain but one contained at least one memory unsafety vulnerability. That is, memory-safe languages would have broken almost all of the chains, even if it wouldn't have prevented all of the vulnerabilities. Analytically, vulnerabilities are a Venn diagram. Those that are only possible in the memory-unsafe language, those that are only possible in the memory-safe language, and those that are possible in any language. In the category of only possible in a safe language, we place things like untrusted eval or use of Python's pickle. Thus far, we think the data conclusively shows that the first category, unsafe languages only, dramatically dwarfs the second category, safe languages only, in magnitude, and there's no reason to think the third category, appears in both, changes depending on what type of language it is. Therefore, it must be the case that using a memory unsafe language increases rates of vulnerabilities. If you think that's wrong, show us the data. The next stage of grief is anger. In anger, people confronted with this problem will claim that while, yes, vulnerabilities can happen in C or C++, the solution is simply to be a better, more disciplined programmer. We argue with this by appealing to the talent of other people, not ourselves. We point out that the engineers at Microsoft and Mozilla and Apple and Google and folks working on the Linux kernel are very talented folks, but they're still beset by this problem. And we try to point out that discipline doesn't scale. My own observation has been that as the scale of a codebase increases, any properties of it which are not programmatically enforced will tend to regress. Put another way, anybody can write a codebase with low bug count but no automated test. But that breaks down as you have more developers writing more code over more time. Similarly, anyone seems to be able to write 100 lines of C code without a vulnerability. No one seems to be able to write 1,000,000 lines of C code without a vulnerability due to memory unsafety. But most importantly, we argue against this with observations from complex systems failure. There's a lot of research on the design of complex systems, such as hospital emergency rooms or the power grid. And there's some amazing folks who look at the overlap between that body of work and things like site reliability engineering work, the maintenance of complex distributed systems. The website how.complexsystems.fail is an excellent presentation of some of the most important ideas from this body of work, from Dr. Richard Cook. Frankly, I wish we could spend an entire session on it. Some of the really important and applicable ideas here are that systems need to defend against failure robustly. If lack of human error is your only real defense, then you have a very fragile system. A power grid has numerous layers of redundancy in contrast. They also point out that our ability to attribute failure to singular root causes is severely limited by cognitive and other biases. I have no problem saying that when a buffer overflow is exploited, that reflects a bug in code written by a programmer, and a gap in mitigations, and insufficient sandboxing, and a fundamental flaw in the programming languages. People who think programmers should simply write bug-free code are denying all of the other contributing causes, not merely the language-level causes. All that said, even if programmer skill were the sole determinative factor in the existence of exploitable vulnerabilities in C and C++, so what? Why would that mean we shouldn't pursue solutions that are resilient to low-skill programmers, who evidently make up the staffs of all of our largest and most successful tech companies? How do we even recognize these types of developers anyway? Is there some way we can screen for them in interviews, make sure we don't ever hire anyone who would write a buffer overflow? Real-world resilient security engineering means, in large measure, we have to take humans as we find them and design systems that work with them, not against them, to produce secure software. The next stage is bargaining. Here we understand that memory unsafety can lead to vulnerabilities, but perhaps we can make this a manageable risk with things like static analysis, fuzzing, sandboxing, exploit mitigation, red teaming, bug bounties. In my view, this is a particularly interesting stage, because the folks making this claim are not wrong. If you're going to have code written in a memory-unsafe language, these are outstanding practices that are necessary to have any level of security at all. Frankly, you probably want these practices with a safe language as well. If I'm writing a browser or operating system, you better believe I'm doing every single one of these. Unfortunately, they're not enough. And the way I know that they're not enough is that the companies that are at the very forefront of each of these techniques are also the ones who were targeted by the exploits I spoke about at the beginning. The Chrome team has tens of thousands of fuzzing cores that they've been running for decades in a distributed fuzzing cluster. iOS was a pioneer in making every single app on the platform sandboxed. Microsoft has invested extensively in memory corruption mitigations, including compiling their entire kernel with control flow guard. And the Chrome team has also pursued an aggressive multi-process sandbox design. Chris Palmer of the Chrome security team is speaking in this very session about security beyond sandboxing. Sandboxing, which has been at the very heart of Chrome's security strategy for more than a decade. And by the way, all of these teams have spent millions of dollars on bug bounties. So yes, if you do these things, you will dramatically raise the cost of exploits against your platform, and that's commendable. But you won't raise them high enough to prevent exploits from being used against human rights advocates, human rights activists, hospitals, journalists, or religious minorities, which is ultimately our goal. At the depression phase, we're now fully comprehending the facts of the situation. Memory unsafety is an underlying cause of huge swaths of vulnerabilities, and it's omnipresent. Tons of critical open source projects, from Linux to Firefox to ImageMagick, have millions of lines of C and C++, to say nothing of the mountains of closed source code. This is just hopeless. Even if we took a year-long break from all feature and bug fix work, we'd barely make a dent in this problem. Maybe there's no point trying to address this cause at all. Just focus on things we can do without rewriting all the code. Fortunately, our problem statement isn't to rewrite every line of code. It's to improve security enough that these types of attacks are no longer practical. And we can do that by working smarter, not harder. The key insight is that not all code represents equal risk, and by prioritizing places that represent the most significant risks, we can do better. For example, the parent process side of a browser's IPC system is a key part of the sandboxing architecture. It needs to be protected. Similarly, kernel device drivers that are accessible from user space are a key attack surface and need protection. On the flip side, a kernel's process scheduler is not really an attack surface we see much in the way of vulnerabilities in, so it's not a priority for language-level safety. When we focus on these, we can achieve incredible leverage and go farther with less effort. These ideas are very overlapping with the ones discussed by Ben Hawks of Google's Project Zero on this very stage a number of years ago. He said that one of their strategies was to find high-contention surfaces and target them with aggressive research in order to break exploit chains. We can do the same thing. If every browser exploit needs a sandbox escape, and if sandbox escapes are overwhelmingly memory-unsafety, then, therefore, we need to focus on those areas as a place to invest in language-level memory safety. It's important to recognize that many modern memory-safe languages allow native interoperability with C and C++ code, no garbage collector, direct calls back and forth, and a shared stack. This goes a long way to enabling incremental migrations to memory safety, rather than requiring us to rewrite the whole world to see any benefits. Acceptance is maybe the simplest stage of all. You stop asking if we need to pursue the work of memory-safe languages, and instead you ask how it is we do this work. You believe that achieving the security goals we all profess to be pursuing is not something that can be achieved with the same tactics we've been using for the last 20 years. You advocate for time and resources to be put towards these efforts within your organization. Now, hopefully through this talk you've reached acceptance. But what do you need to do specifically to bring out the more secure software we all hope for? First, within your own organization, find the other folks who feel the same way. Language-level solutions to memory-unsafety will impact every single person who works on your product and its infrastructure, so you need to get a posse to advocate with you. Next, find a memory-safe language that'd be a good fit in the places you currently use unsafe languages. Earlier I suggested a few good pairings of languages with use cases. Go for network services, Swift for Apple ecosystem development, Rust for interoperability with existing C and C++ code. But there's plenty of other good choices and good pairings too. Now, do the work to make it possible for teams and projects that want to use this language to be able to do so for real projects. This often means improving build systems, testing systems, and release processes to be able to handle a second language as easily as they handle your primary one. It also may involve building critical utility libraries. If every project in your organization needs to talk to some internal API, you'll want an SDK for using that API in your new language. Finally, get to work, building new components in the safe language, and where high leverage, replacing existing components. Generally speaking, you want to replace chunks that are as small as possible without dividing your software into incoherent pieces. If your organization doesn't have memory-unsafe code of its own, you're still likely using things written in a memory-unsafe language via open source or closed source projects you use. Going forward, you should take what language is this written in into account when choosing these components. Perhaps it'd be better to use an authenticating and authorizing HTTP proxy written in a memory-safe language rather than one written in a memory-unsafe language. Lest you be stuck at the depression phase, unsure of how any of this can be tractable, I want to close with a few examples of projects that are doing this in the real world. The Python Cryptographic Authority, which I help maintain, and which develops the most widely used cryptography libraries in the Python ecosystem, has been doing gradual work to replace code written in C with Rust, starting with some subtle constant time code, and shortly extending to cover a bunch of ASN1 parsing code. The Rust for Linux project is working to make it possible for people to write Linux kernel modules in Rust and getting that support upstreamed into Linus's tree. Firefox has been engaged in a long-term effort on this front, which has included rewriting existing components, such as its CSS engine, as well as making it possible to build new components in Rust. For example, its WebAuthn support was built with Rust, a real addressing the root causes 2-for-1. Finally, librsvg engaged in an effort to rewrite their existing C code to Rust in an incremental manner, and now the project is almost entirely safe Rust. There are, of course, many other successful efforts using different languages at adopting memory safety. These are just a few which prove it can be done, and which prove your project can be next if you begin the work. Before we finish, I want to share some nearly 2,000-year-old wisdom. It is not incumbent on us to complete the task of ridding the world of memory unsafety, but neither are we at liberty to desist from it. Thank you very much. I'm now happy to take questions.